Hello, good afternoon everybody. Today I will take class on free radicals. Okay. So free radical is a species containing one or more unpaired electrons, each with a magnetic moment and spin quantum number. So I write down here a free radical is a species containing one or more unpaired electrons. More unpaired electrons. Okay. So they have each of the electrons having a magnetic moment. Each of them you can say have a magnetic moment. Has a magnetic moment, and the spin quantum number, is either plus half or minus half. Okay. So I'm repeating again. So a free radical is a species containing one or more unpaired electrons. Okay. Unpaired electrons, each of them having with a magnetic moment and spin quantum number either positive or negative. They are represented by dot. Okay, like this dot, and their stability depends on the conditions, reaction conditions, and they are generally mostly short-lived, and they can be detected by electron spin. They can be detected by ESR, electron spin dissonance. Okay, electron spin dissonance, or you can say EPR, or you can say EPR, electron paramagnetic resonance, electron paramagnetic resonance. Okay, resonance spectroscopy, ESI spectroscopy, or you can say EPR spectroscopy. So they can be detected. Okay, so I'm repeating again, a free radical is a species containing one or more unpaired electrons, each with a magnetic quantum number and spin quantum number, having a magnetic moment and a spin quantum number either plus half or negative half. They are represented by dot, and they can be detected by electron spin resonance or electron paramagnetic resonance. So they can be we can differentiate from carbocations, carbon ion, like that. They can be differentiated from carbon ion or carbocation. So free radicals can be, let's say, suppose these are free radicals. Let's say this was free radicals. Okay, this is free radicals. So when you this are the reduction of this one, reduction, something means addition of electrons. This will give negative charge. One electron will come. So here negative charge. Okay. So here then this is carbon ion. They call it carbon ion. And this let's say R. Okay. And we will oxidize this one. When oxidation of these free radicals, this is free radical, represented by dot. Okay. When oxidation means removal of electrons. So you get one electron is removed, so it becomes positive charge. Okay, carbocation. Here. Carbocation. So difference between among these three species, free radicals, when you use reduction of the free radical give the carbon ion, and oxidation of the free radical will give the carbocation. Okay, carbocation. So here around the valence electrons are 6 valence electrons. Here in the carbocation 6 valence electrons. Okay, valence electrons. But in the case of free radicals, there are 1, 2, 3, 4, 5, 6, 7. Okay, this free radical have 7 valence electrons. And in the case of valence electrons. Okay. But in the case of carbon ion, there are 8. So 8 valence electrons. Okay, so we can differentiate in this way by free radicals among carbon ions and then carbon cations. Okay, so I'm repeating again. Free radicals, or free radicals, the rejection of the free radicals gives this carbon ion, and oxidation of these free radicals gives carbon cations. So now let's have structure of free radicals. Let's have this. Now let us have structure of free radicals. Okay. Structures of free radicals. Free radicals can have either two types of can be possible structures of free radicals. So free radicals can have two types of structures, either sp2, two types. There may be two types. So first one is a sp2 hybridized. So let's say sp2 hybridized structure. Let's say A hybridized planar structure. Let's say is A. Okay. Yeah. Another one is another can have sp3 hybridized pyramidal structure. Okay, then structure. This side is B. Okay, so I can draw here the structure of this free radicals as like this. So we can have, suppose this is one. So let's just say this is free radicals. Okay, so you can have this one. It can be dot, and so I have another empty 2pz orbital. So they have these free radicals. So here the planar sp2 is structure A. This is planar sp2 hybridized planar. Okay, and here is unpaired electron occupy this empty. Yes, 2pz orbital. Okay, empty 2pz orbital occupied by this electron, unpaired electron. So this is you can say sp2 hybridized. Excuse me. sp2 hybridized planar structure. sp2 hybridized planar structure. Another one, they can have this form. Okay, this is a sp3. Another one, so let's say, and then another one is like R. We can have this one, R, and then R. Okay, or sp3. I will. That's why the another sp3 here. So we occupy this position electron here. So this is structure V. So here sp3 hybridized, and this is pyramidal type. Okay, pyramidal structure. Okay, so I will put it again. Okay, free radicals can have two types of structures. One is sp2 hybridized planar structure. Second one is sp3 hybridized pyramidal structure. So in these two cases, generally structure A is more stable, probably mostly exists in this form by calculation, by static determination by ESR or APR. And generally they are found to be sp2 planar. Okay, planar structure. They are found as planar structure, like CH3 methyl radical. CH3 groups is also found as structure is found CH3 methyl. Okay, methyl radical is usually found as this sp2 hybridized planar structure. So now this is about the structure of free radicals. Now let us have this generation of free radicals. So free radicals can be generated by thermolysis, photolysis, or decomposition reactions. So let's say generation of free radicals. Generation of free radicals. Okay. Free radicals. So free radicals can be generated by pyrolysis, or you can say by thermolysis, or thermolytic fissions, and photolysis, or by decomposition reaction, or by decomposition reactions. Decomposition reactions. Okay. So I'm repeating again. Free radicals can be generated by free radicals can be generated. Physicals can be generated by thermolysis, or you can say thermal cleavage or photochemical cleavage and electromagnetic reactions. So let's see one by one. Thermal cleavage. Okay. So here take the by homolytic fissions. So radicals are generated by homolytic fissions. Many examples are here by thermal cleavage. For example, say azo compounds. So this is the azo compounds. Okay. So by you can say by heating thermal cleavage. So it is photo. So one go they represented by this raw like this, and this, and this one, half a fish hook. Okay, they are fish hook. So here we got 2R radicals plus nitrogen. Okay. So this is by heating at high temperatures we got this thermolysis, thermal cleavage takes place. So it is homolytic cleavage. Another example is benzoyl peroxide, so phenyl, COO peroxides. Okay, COO phenyl by heating at high temperatures. So you can give phenyl, COO, then plus. Okay, here this one. This will go like this. Another one will go like this. Okay, we got two. So benzoyl peroxide. This is benzoyl peroxide. Benzoyl peroxide can undergo thermal cleavage at heating by high temperatures to give this radical. Okay, benzoyl radical. Another one azo compound. This is azo compounds. Azo compounds can undergo thermal decomposition also. So okay. So this is the first one. So generation of free radicals can be generated by thermolysis. That means thermal cleavage at high temperature. Some examples are azo compounds, as well as benzoyl peroxide. And again, second one is by photolysis, or you can get photolytic cleavage. Okay, by photolysis. So free radicals can also be generated by second one by photolytic cleavage. Okay, or you can say photolysis by this thing, by using light. So some compound, for example, say chlorine. Okay, chlorine molecule. So you can have by using light, then you can have this one like goes and this one goes. So you can have this one. Okay, you can have two chloride radical. Okay, that is another example. Ketones, like ketones, they can have the light, so they go one go this way, another one go this way. So you can have RCO radical, and another one is R5 radical. Okay. So this way by photolytic cleavage. So they are mostly homolytic fission. Sorry. Then third one is by decomposition reactions. The free radicals can also be generated by decomposition reactions. So for here in this case, a radical can undergo, for example, a radical can undergo photolytic by photolysis or any other method here. So these are free radicals. Okay. So you can go to get another free radicals here this way. So here this one and this one, let's say here. So in this way the arrows are fish hook arrows. So now this phenyl group becomes radicals and this becomes carbon dioxide. Okay, CO2. So free radicals can give another free radicals by decomposition reactions. That's why these examples. So I'm repeating again. So free radicals can be generated by three types. First one is by thermal cleavage, second one is photoelectric cleavage, and third one is decomposition reactions. Now let's see the stability of free radicals. Stability of free radicals. Just like carbocations, stability of free radicals depends on their generally their depends on their hyperconjugation, inductive effect, and resonance effect. So let's see now this stability of free radicals. Okay, free radicals. So free radicals can be depends on the this stability depends on the like just like the carbocation depends on the effect, hyperconjugation, and resonance effect. So stability of radicals are almost similar with the stability of carbocations. So it depends on inductive effect, and then you can say hyperconjugation effect, and then another one is resonance. Okay, you can say canonical structure resonance. So hyperconjugation means generally the radicals are not the tertiary radicals are more stable than secondary and then primary. Okay, so you can say by due to inductive effect or by hyperconjugation effect, these tertiary radicals are more stable than than secondary free radicals and primary free radicals. For example, so let's say this CH3, then CH3, okay, this CH3, this tertiary free radicals greater than CH3, this secondary free radicals and greater less more than CH2, CH3. This is primary or greater than CH3. So some of the primary, okay, primary free radicals, so primary free radicals, the secondary free radicals, and tertiary free radicals. So what I want to say that in the case just like carbocations, free radicals, the case tertiary free radicals is more stable than secondary free radicals, and then primary or CH3. This can be explained by hyperconjugation. More hydrogen atoms can be conjugated. So you give 9. There are 9 hydrogen atoms, so it can be give 9 canonical structures. So you can have more stable, more canonical structures, resonance structure, then give them more stability of the free radicals. So you can have 9 structure here, and 6, here 3, and then no structure. So no hyperconjugation structure. So here 9, 6, 3. So more resonance structure will give them more stability of the free radicals. So this is hyperconjugation. Now by resonance also, by resonance also you can have the conjugated with a double bond, and be more stable. If the free radical is conjugated with a double bond, then they will be more stable. For example, say you can compare allylic or vinylic. So let's say this one. Okay, this is radical. Okay, another one is this is CH3, CH2. This is CH2, CH the other. So here, this is more stable than this one. Okay, because of the you can write this way and this way. Okay, so you can write this structure. So you can have this one. This one radical here from one radical, one electron from here, and the electron from here. So you get the bottom one. And one electron goes this way, that's why it becomes radical. So you can have 2 resonance structures, but here no resonance structures. So that's why this more stable than this conjugated. Here conjugated, not conjugated double bond. Similarly, you can have say these are okay benzene radicals here. So it's more stable, and then again they are more stable. This one CH3. So for example, let's say they have so many resonance structures they can write, or you can have another one is CH3 resonance, this one, and this one more stable than this cyclohexyl, okay, cyclohexyl like this. So they comparing this because they are conjugated with the bubble, more resonance structure is more stable. So like in the case of carbocations, so what I want to say, if they are conjugated with a double bond or multiple bond, then happy radicals are more stable. And another one is that by hyperconjugation, so they are also more stable. So more resonance structures, more stability of the free radicals. Okay. So now another destabilize also, destabilization of the free radicals will be more. If they are, another factor is that if they are more X character, they are less stable. Okay. So here let's say this is CH3 ethyl. Okay, radical is more than this benzyl CH2, the one CH. Okay, radical, and this one is another one, C triple bond. C is okay. So that means this is more stable than this. Yes character here is higher, this character is less, here also very less. So with the increase in the S character, the stability also decreases. Okay, free radicals. So I can write down free radicals. Decrease in stability. Free radicals decrease in stability with the increase in S character, or with the increase in S character. Yes, as you can say with the increase in percentage, you can percentage of S character. You can say percentage of S character, S orbital character. Okay. Character. Okay. So physical decrease in stability with increase percentage of S character. So here percentage of S character is high to increase. So here increases S character increases, but stability decreases. Okay. So this is one factor of this destabilization of the free radicals. Another factor is that across the periodic table, free radical decrease in stability as electronegativity increases. So another factor is that across the periodic table, the stability of free radicals, another factor. Okay, decrease in stability. Stability of physical decreases. You can decreases as electricity, and stability of physical decreases as electronegativity increases. Negativity increases. Okay. Higher electronegativity, lower stability of the free radicals. So you can compare this one H3, C, methyl, then you can compare nitrogen, more electronegativity. So you can have, so here, then hydroxy groups, O, again here, and then finally this fluoride. Okay, like this. So this table, so increases polarity, the electronegativity increases the carbon, nitrogen, oxygen, fluoride. Okay, so increases the electronegativity, but the stability of this particle decreases. Okay, another third factor, another is the destabilization of the free radical. And third one is that if the free radical increases with the increase in the periodic table. Okay, so I'll show you here again. Radical increase in stability going down the down the stability going down a column of the predictable. Okay, so you can say physicals increase in stability, okay, with going down the column of a predictable, okay. So for example, you can say fluorine, fluoride, this is chloride, bromide, and iodide. Okay, physicals. So iodide is more iodine physical more than bromide, chloride. This is just fluoride. So electronegativity is higher when you in a column fluoride, chlorine, bromine, iodine, like this. Okay. Down the column, so stability increases. So here stability increases and this stability is less in the predictable. Okay. So another factor, there are three factors to destabilize the physical. First one is the increases S character, and second one is the electronegativity. Increase in the electronegativity, stability of the particle decreases. And third one is the particles increase in stability when going down the column of a predictable. Okay, so this is third one. So this is about the physicals. So in the next class I'll take down about the reactions of physicals and so on. So today about you discuss this much. Okay, here we'll wind up here. Next class I'll take the reactions of physicals. Okay.